Welcome to this brief demo of what's new in the 2004A release of Agilent's Advanced Design System. This is a shameless product pitch, so to thank you for taking the time to watch, at the end of this presentation you'll be able to enter our weekly drawing for a combination 256K USB memory stick, MP3 player, digital voice recorder. It's pretty cool. So let's get started. Our main focus with this release was to improve the ease of use and productivity for circuit design applications. In other words, we wanted to make common tasks easier to do. The first task I'll show you is tuning. I'm going to demonstrate the speed and user interface improvements we've made to tuning with this filter circuit. We will be tuning the variable X, which scales the values of the L's and the C's in this circuit. This is the new tuning user interface here. The step size, minimum, maximum, and current values of X are shown in these boxes. As I move the slider, the circuit performance updates in real time. We are tuning with 80 frequency points and can sweep linearly or logarithmically. Having the choice of a linear or logarithmic sweep can make it easier to tune rapidly changing circuits. I've been using the slider in continuously varying mode, which can yield component values with many digits of resolution. Clicking Snap Slider to Step forces the slider to vary only by the step size, which can yield more realistic or manufacturable values. I can save a trace by clicking Store. This dialog box allows me to name the memory trace and automatically includes the value of the parameter being tuned. The values are shown in the plot legend. This is very useful for documenting the effects various component values have on circuit performance. If I want to tune another component, I can go back to the schematic and select the component I want to tune. For instance, this capacitor is not being tuned. To tune it, I just click on it. A slider appears, and now I can move the slider and vary the value of that capacitor. If I click Update Schematic, the schematic is annotated with the new tuning parameter value. This is new. I no longer have to configure tuning every time I want to use it. It's saved with the schematic. Now, tuning is not limited to linear simulation. Let's take a look at something more complicated. We'll use this amplifier circuit and perform a DC and harmonic balance simulation. The parameters we can tune are the gate voltage step size, the output load resistance, the drain voltage bias point, and the RF input power. What is displayed is the dynamic load line, the spectral content of the output, and the input and output waveforms. You can see the spectral content change with input power, the waveforms clipping, and the changes in the load line as I tune various parameters. We're tuning a complex simulation with a great deal of information being made available, and the results are displayed in real time. I could show you tuning a component in a subcircuit or tuning using a complex modulation signal and showing the resulting eye diagram, but enough about tuning. Hopefully you can see the tuning improvements we've made. Another objective of the 2004A release was to improve the ease of use for new and infrequent users. So the first thing you notice when you launch ADS is the new greeting dialog. It asks, do you want to create a new project, work on an existing or recently used one, or open an example project. It also has a link to the Quick Start manual, and you can easily disable this dialog if you don't need it. I'm going to create a new project and name it Filter. Here you see the next improvement, a new schematic wizard that comes up automatically whenever I launch a new schematic window. It can be permanently deactivated if I want. By asking a series of simple questions, the schematic wizard will set up a schematic page with a simulation and a sample circuit to get you started. I'll set up a simulation. From these various application types, I'll choose a 2-port application. For a sample circuit, I'll choose a lumped element low-pass filter. And we'll use a linear frequency sweep. Useful instructions on how to complete the design are shown. I'll close this window, and as you can see, a subcircuit was created and terminated. I'll select the subcircuit and push into it using this button, and you can see the sample circuit here. At this point, I could modify this circuit or replace it and begin designing my circuit. To simulate, I'll return to the top level menu and click the Simulate button here. When the simulation completes, the pre-configured data display window appears. So, we've launched ADS, set up a simulation with a sample circuit, and gotten results, all in a matter of minutes, and it was easy. In addition, you've seen how fast ADS is from the time I clicked Simulate to the time results were displayed. This simulation button down to data display up time improvement makes the whole product feel more responsive. This table shows how much faster the 2004A release is compared to the 2003C release on various platforms and for various circuit sizes. By the way, this table also shows that we now support the Linux platform. I'm showing here the improvements in linear simulations. As part of an ongoing effort, harmonic balance simulation times also improved. On this chart, you can see that harmonic balance simulation times on Windows are about twice as fast compared to our 2003A release, and even faster on Unix machines. Speed is not the only improvement we made and continue to make on our simulators. In the interest of time, let me just say that we have automated our transient assisted harmonic balance simulation, improved phase noise analysis to provide a single accurate result, have faster Krylov solver times when simulating oscillators, and have made improvements in memory management that allow simulation of larger circuits with the direct harmonic balance simulator. That's a mouthful, but it gives you some idea of the powerful simulation improvements we've made in this release of ADS. Let me talk now about the significant improvements in layout. We now have a new physical connectivity engine integrated in layout with real-time interconnect extraction, which means that electrical interconnects are created while you design in layout. With this capability, you can show the physical interconnections by clicking on any component, trace, or polygon to see everything electrically connected to it. This allows you to quickly find connections and possible errors. The new physical connectivity engine also improves our check design tool. This tool checks a layout for 8 categories of possible errors, including the 2 errors shown here: open connections and shapes touching but belonging to different nodes. Clicking on the error highlights the problem area of the layout. I can select auto zoom, and when I click on the error, it zooms in on the problem component. This is very useful when dealing with large layouts. In this case, this component is not properly connected, so I'll move it to connect the nodes. I refresh the design checker, and we no longer get an error. We also have moved several commonly used tasks to a new layer selection window that allows you to choose the layers you want to be visible, which ones you want to be selectable, and to quickly change the current layer by simply clicking on the layer you want to be active. There are many more usability improvements in layout, but before we finish, I want to show you a new tool in ADS called RF System Budget Analysis. Budget analysis allows you to design a circuit using high-level functional blocks such as those shown here. This allows you to determine or budget the performance needed from each component to achieve the desired system performance. The budget controller in ADS has over 80 budget measurements. If I double-click on the controller, you can see the measurements here in this column. And select the measurements you want by placing them here in the right-hand column. Budget analysis results can be output to the data display, where you can see the results of each component in a table or using a graph. Here you see the gain and output power of the filter, amplifier, mixer, filter, and final amplifier. Results can also be output to an Excel spreadsheet. All of these graphs and tables were automatically created using an Excel macro that ships with the advanced design system. Let me finish up by listing just a few more improvements to ADS. You can see the list of improvements is long and includes things like better modeling of thick conductors by our planar electromagnetic simulator, a new UWB OFDM design guide, accounting for self-heating in the Agilent HBT transistor model, and many more improvements that would be extremely boring to listen to, but you will appreciate having when designing with the advanced design system. Well, we've reached the end of this brief overview of the ease of use and productivity improvements in the ADS 2004A release. For more information, you can visit the Agilent eSoft website or give your local Agilent eSoft salesperson a call. If you're connected to the web, you'll now be taken to a website where you can enter our weekly drawing. Thanks for listening, and good luck.